let's go ahead and take a journey. We have in this code class talked a little bit about the derivatives of one trig function. I believe we talked about the derivative of sine. And you can either, we did the limit definition. We also talked about a graph of it. So I'll remind you all, sine of x looks like this. It's being very kind of loosey-goosey about it. You know, when you're a young person, you don't think you'd be saying loosey-goosey all the time, but like as an older, I mean, it's loosey, like I'm not a fan of me saying that, but this is where we've gotten to. So yeah. So here's your sine function. And one easy way to kind of think about how to graph cosine, or sorry, its derivative, I know I gave away the answer, oh well, such is life, is to think about the slopes of the tangent. So this function has a slope of +1 right there at the origin, a slope of 0 at pi over 2, a slope of -1 at pi, and a slope of 0 at 3 pi over 2, and then back to 1. So if we graph those slopes, plot those slopes, I should say. So here's our slope of 1, slope of 0, slope of -1, slope of 0, slope of +1. We get exactly what we were expecting, which I already gave away, which is that the derivative here is cosine of x, if your original function is sine of x. And you can do that again, right? We can use the same sort of graphical idea to say, well, if I look at the slope of the tangent lines here, slope of the tangent line is 0, -1, 0, 1, 0. So then we're back to something that looks kind of like sine. I mean, really sine and cosine, same function. They're just shifted from each other. They look very similar. They're both called sinusoidal functions, but they're kind of the same. But if you take the derivative here, you get back to something kind of like what you started with, except it's flipped over. So we get 0, and then we get -1, and then 0, and then +1, and then 0. Not that point down the x on the graph. And this looks a lot like the derivative of cosine, which it is, which is negative sine of x. I would like to show you all just one more time. Well, actually not one more time. So we did the derivative of sine of x, the long limit definition way a class or two ago. I also would like to show you the limit definition derivative of cosine, just to kind of be complete about it. So if I want to find the derivative of cosine of x, kind of the long way, we can use the limit definition. Say, okay, it's going to be the limit as h goes to 0 of cosine of x plus h minus cosine of x over h. And just like when we did this for sine, we're going to have to use the angle sum formula. So, excuse me, cosine of x plus h is equal to, also, if you don't want to write this part down, you really don't need to. No one's ever going to ask you to do this. I just want to show it to you so you can, again, believe, even though we've seen it graphically, that the derivative of cosine is sine. So I'm going to say cosine of x plus h is cosine of x times cosine of h minus sine of x times sine of h. That's the angle sum formula for cosine. Cosine of a plus b is cosine a plus b minus sine of b. And then minus this cosine x still. And then we do the same sort of thing we did for the sine one, which is we group the two pieces together that have a similar thing. I see a cosine x there and a cosine x there. So we're going to write this as the limit as h approaches 0 of, we've got these two pieces, so cosine x times cosine h minus cosine x all over h. And then we've got this other piece, minus sine x times sine h all over h. And here's where we start to make things look like things that we have seen before, meaning I'm going to factor out a cosine x from here. So I'm going to write this as the limit as h goes to 0 of cosine of x times cosine h minus 1 over h. And here I'm going to bring out the sine of x and see that I'm left with a sine of h over h. Now, I've seen this a couple times. As h goes to 0, what's the limit as h goes to 0 of sine h over h? The 1. That's going to go to 1. How about the limit as h goes to 0 of cosine h minus 1 over h? That one's a little less familiar, but we have seen a couple of times that that limit is 0. And the way you can get there is by multiplying by the conjugate. can multiply this by cosine h plus 1 over cosine h plus 1. Eventually you get 0 over 2. So look what we're left with. We get cosine x times 0 minus sine x times 1, which is equal to negative sine of x, as expected. So the derivative of cosine of x really is negative sine of x. Derivative of sine of x really is cosine x. And now what we're going to do, just to kind of be complete about it, so you aren't like wondering later, let's just find the other 4 trig derivatives really quick. They're really easy to do once you know these first 2 because we're just going to use the quotient rule. So let's do the other 4. And we're going to make a little list, and I do encourage you to make this list in the following order. It's a pretty standard way of writing it. So we're going to write down the derivative of sine of x is equal to cosine of x. The derivative of cosine of x is equal to negative sine of x. And we're going to do the derivative tangent of x, and we'll fill that in a moment. And then over here on the right-hand side, we're going to write the reciprocal functions. So the derivative of cosecant of x, we're going to find the derivative of secant of x, and the derivative of cotangent of x. I guess we put some parentheses. You don't really need these parentheses, but it's not long. So for the derivative tangent, question. Of the inverse trig functions? Yes, at some point. Maybe not yet, but we will certainly learn them at some point. Oh yeah. Okay. We might be able to get there today, but we've got a few other things to get through first. So derivative tangent, you're going to write tangent as in terms of sine and cosine. So we write the derivative tangent as the derivative of sine x over cosine x. And then we're going to use the quotient rule, right? Because it's a quotient. So we're going to do the bottom times the derivative of the top minus the top times the derivative of the bottom, all of the bottom squared. And I know there's other ways people say it. That's how I like it. But you can say low d high minus high d low over low squared or whatever floats your boat. So we're going to have the bottom times the derivative of the top, and the derivative of sine is cosine, minus the top times the derivative of the bottom, the derivative of cosine is negative sine, all divided by the denominator squared. And if we simplify this, we get cosine squared x plus sine squared x all over cosine squared x. And this is where we use our favorite trig identity, which is that cosine squared x plus sine squared x is equal to 1. So we get 1 over cosine squared x, or more typically written, secant squared of x. So there's the derivative tangent. You definitely want to memorize that. The derivative tangent is secant squared of x. And actually, yeah, we'll do that. So let's do the derivative of cotangent x because it works out very, very similarly. So for cotangent of x, there's a sine over cosine, it's cosine over sine. Same deal. So you get cosine x over sine x, and then that's going to be the bottom times the derivative of the top, which is negative sine x, minus the top times the derivative of the bottom, which is positive cosine x, all over the bottom squared. And now you almost have the same thing as before. It's a little different. You have negative sine squared x minus cosine squared x all over sine squared x. If you factor out a negative 1 from the top, you have negative 1 times sine squared x plus cosine squared x, which is just negative 1 times 1. So again, we see that trig identity. This top part is just negative 1 over sine squared x, which becomes negative cosecant squared x. There is a nice little pattern here, which I'm going to mention as soon as we finish off our list. At least there's a pattern as far as I'm concerned. So let's do the last 2. Let's do the derivative of secant first. So for secant's actually maybe easier. I don't know, maybe not. So we're going to write secant as 1 over cosine, and then we're going to use the quotient rule. So it's going to be bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is negative sine, all divided by the bottom squared, which ends up equaling positive sine of x over cosine squared x. And although that's totally correct, it is not the way anyone ever writes the derivative of secant of x. So even though that's right, what we're going to do is we're going to fix it. Let me move this cursor out of the way. We're going to re-express this as 1 over cosine x times sine x over cosine x. And then we're going to rewrite each of those as secant x times tangent That's how people typically write the derivative of secant. So the derivative of secant x is secant of x times tangent of x. Now here's what I would like you to see before we do the last one. There is a nice pattern here, in my opinion. And the pattern here the pattern kind of works this way. Sine and cosine, you just need to know. Derivative of sine is cosine. Derivative of cosine is, you could actually say it's cosine. The co-function of cosine is sine. There's a reason I'm saying that. It's not just because I'm trying to make sure. So it's negative sine x. Okay, here's where the pattern starts to happen. The derivative of tangent is secant squared of x. And now what I'm going to do is I'm going to take both of those trig functions, tangent and secant, and put a co in front of them. The derivative of tangent is secant squared. The derivative of co-tangent is co-secant squared with a negative sign. The same sort of thing works here. Check this out. We haven't found it, but I'm going to tell you the derivative of secant is secant times tangent. I should really say x. The derivative of secant of x is secant of x times tangent of x. The derivative of co-secant is, instead of secant, I'm going to get cosecant of x times, but of course it's going to be negative. And I know it's going to be negative, and you know it's going to be negative, because what we see is that every co-function, cosine, cotangent, cosecant, every co-function has a negative derivative. That is a true fact for trig functions. I will point out it is not true if you're talking about the hyperbolic trig functions, because they're not really trig functions. They just act a lot like trig functions. If we might not even talk about those. I certainly didn't learn them when I took 21A. I used to do this, but some people do cover them. So if we need to cover them, we will, but often they get kind of skipped over. They're not that important. So you could also find the derivative of cosecant the long way. Derivative of cosecant of x is indeed the derivative of 1 over sine, which is bottom, times derivative of top, minus top, times the derivative of bottom, all over the bottom squared, which ends up being negative cosine x over sine squared x, which we can write as negative 1 over sine x times cosine x over sine x, which is indeed negative cosecant of x times cotangent of x. Cool. So there's your 6 trig derivatives. You definitely know them. You definitely want to know them. You definitely need to memorize them. They're going to come up so much that you're not going to be able to help yourself to memorize them. What I've recommended to people in the past who've had trouble memorizing them is to make it the lock screen on your phone. So whenever you look at your phone, they're right there. And you just can't, like, that's what I have done in the past for other mathematical things I've had a hard time memorizing, is making them the lock screen on my phone. So every time I'm like, oh yeah, remember that? Oh yeah. One other trick a student showed me that they came up with for memorizing these was the following. And I thought this was kind of slick. Sine and cosine, you kind of, right? They're going to be there all the time. Derivative of sine is cosine, derivative of cosine is negative sine. For the other 4, you can do this. I like this pattern I just talked about, but I had a student show me this one time, which I thought was kind of slick. They would always write this. They would say, I don't know how to do it. Yeah. They would write tangent of x, right arrow, secant of x, left over arrow, secant of x. So that they would say, okay, the derivative of tangent is secant times secant. Checks out. Derivative of secant is secant times tangent. Checks out. And then they would do the same thing for cotangent of x, negative cosecant of x, cosecant of x. The derivative of cotangent is negative cosecant times cosecant. Checks out. Derivative of cosecant is negative cosecant times cotangent. Checks out. So that was something they did that I think was crafty. I never would have thought of that, but they did. I was like, oh, that's cool. That's a good idea. So lots of different ways to remember the derivatives of trig functions, but we do need to remember them once your class has covered it. You can then or even if you haven't seen it yet, you still know. Questions so far about this? Yeah. I mean, they could. Well, so here's what I would say. All of these functions, like many functions, the majority of functions we will encounter in this class typically are both continuous and differentiable on their domains, meaning where they're defined. So sine and cosine are continuous everywhere, differentiable everywhere. Tangent, cotangent, secant, and cosecant are continuous on their domains, meaning everywhere they're defined, so everywhere they don't have a vertical asymptote, and they're differentiable on their domains. Again, everywhere they're defined. So yeah, most functions we encounter are typically continuous and differentiable on their domains. There are some exceptions though. In fact, it's a good question. So some exceptions. So two of my favorite functions that are continuous everywhere, but not differentiable everywhere. So I would start with this function. Here's a function that is definitely continuous everywhere, right? You can graph it without lifting your pencil off the paper. So f of x equals opposite of x is continuous everywhere, but it's definitely not differentiable everywhere. As I would like to encourage you all to think of, not that it's 100% true, but when you think about differentiability, if you're trying to think of like the layman's terms, it's like how continuity kind of corresponds to being able to draw the graph without lifting your pen off the paper. You should think of differentiability as smoothness. So if the graph is smooth, aka not pointy, it is almost always differentiable. There's an exception, which we'll point out, but this graph certainly does not meet the smoothness requirement. Absolute value of x has a pointy point, the vertex at the origin, right? It looks like this. So this function is definitely so I would say, even though it's differentiable almost everywhere, in fact, everywhere except for at x equals 0, I would still say this function in general is not differentiable. Because if you're not differentiable everywhere you're defined, typically that means we're thinking of you as being not differentiable. But really, to be more precise, is differentiable everywhere except for 0. Usually, if you're trying to say a function is differentiable, you're saying it's differentiable everywhere it is defined. And this function doesn't meet that criteria. Not differentiable at the origin. How do you show it's not differentiable? You have to use the limit definition for 0. So you want to show that f prime of 0 does not exist. So you have to do, okay, f prime of 0 is limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. And then that ends up being the limit as h approaches 0 of the absolute value of 0 plus h minus the absolute value of 0 all over h. And then you have to do the two-sided limits. Right side is going to be positive 1, left side is going to be negative 1, which makes sense because the slope on the right side of this graph is positive 1. The slope on the left side of this graph is negative 1. So we definitely have, oh yeah, the limit as h approaches 0 from the right is just the limit as h approaches 0 from the right of h over h, which is the limit as h approaches 0 from the right of 1, which is 1. Whereas the limit from the left of absolute value of h over h, well, if h is negative, because we're left of 0, then the absolute value of h is negative h. And negative h over h is negative 1, and the limit of negative 1 is negative 1. And those don't match. No. So we don't get the derivative existing in 0 because the limit definition of the derivative does not exist. So right, if this limit doesn't exist, that means this derivative that is equal to that limit does not exist. So f prime of 0 does not exist. Yeah.
As a really quick aside, should when we can actually divide 0 by 0 and when we can? Because I know there are situations where
I cannot. So the thing is, 0 over 0, indeterminate form. A lot of the time you get various things. Some of the times it ends up not existing. So it really depends.
So here, how did you know that it was equal to 1? If you have the graph and you have everything else, if it was just h over h, do you just know it because?
Well, so what I would generally say is that you're always allowed. So what we're saying here, right, is h isn't equal to 0. H is really close to 0. But if h isn't 0, if h is like 0.000001, then 0.000001 divided by 0.000001 is a totally valid operation. I can divide not 0 by the same not 0 and get 1. So I'm allowed to do all the usual algebra things I would normally be allowed to do. I'm just doing normal algebra, saying, oh, h divided by h, that's 1. So yeah, but the point here is, right, this is 1, and then this is the one, and then it doesn't exist because they're not the same, not because there's some other magical 0 over 0 weirdness happening. So yeah, typically, if things cancel, we're allowed to cancel them.
Unless you have something like 2 minus x as example. 2 minus x divided by 2 minus x as example, just 2.
No, we would totally be allowed to do that too. So if you had the limit as x approaches 2 of 2 minus x over 2 minus x, that limit's 1. Or if you want to be more precise, it's the limit as x approaches 2 of 1, which is 1. Here's what this graph looks like. This graph looks kind of dumb. It's totally fine. Not every graph is wonderful. I mean, I guess I could be more inclusive. Every graph is wonderful. But this graph is equal to 1 all the time, except when? When is this graph definitely not equal to 1? When x is 2. Because if you plug in 2, what do you get? You get a hole. So what's happening here is at 2, this graph is not existing. So here is the function x minus 2 divided by x minus 2. The limit totally exists and is equal to 1, but the function is not defined at 2. Right. But much of the time we can't. Yeah, I don't have a good example where we can't. So 2 more examples of functions that are continuous but not differentiable on their entire domain. Here's my next favorite one, which is my next favorite one. Yeah, this is good. F of x equal to x to the 2/3. Or as I like to say, I like to call this the bird function. Why? Because it kind of looks like a bird a not artistic adult or a young child might draw, like that. Like those little birds, right? Like they're going off. Imagine some of you have drawn a bird like this once in your life. The function x to the 2/3 looks kind of like that. It does this sort of deal. And just looking at the graph of it, it's looking pretty pointy at the origin. What I would say is this previous function has what's called a corner at the origin. This function here has what's called a cusp at the origin. But either way, whether it's a cusp or a corner, it's a pointy point. And pointy points are not differentiable. I know, right? Pointy points. But here's how you'd show it's not differentiable at 0. So here it's actually a lot easier. If I take the derivative is 2/3 times x to the negative 1/3, just using the power rule. And simplifying that, we're rewriting it. It's 2 over 3 times the cube root of x. And if you try to plug in 0, it's not a 0 over 0. It's a not 0 over 0, which means the limit does not exist. If you plug in 0 here, you get 2 over 0, which that doesn't exist. This function definitely is not differentiable at 0. It's got something that's approaching you. Oh, no, it doesn't. No, I shouldn't even say that. It's not true. This function does not have a tangent line at 0. Because you've got kind of weird, right? From the left, you've got tangent lines with slopes that are increasingly negative. From the right, you have tangent lines with slopes that are increasingly positive. And those slopes aren't going to be approaching each other. Right? If I was going to look at right, if I looked at my derivative being this, if I said the limit as x approaches 0 from the right of f prime of x, I would be getting positive values. Right, this is one of those number over 0 situations. If I plug in a positive 0, cube root of a positive number is positive. Positive over positive is positive infinity. So this limit from the right certainly is positive infinity, and the limit from the left is negative infinity, which means the overall limit wouldn't exist. Okay, so far, these aren't terribly disappointing. Neither of these look like they should have been differentiable anyway. Yeah. Sure. Yes. So looking at this next one is where things are, in my opinion, sad. This function, f of x equal to the cube root of x. It looks lovely. It looks like, I'm never good at drawing this one, but we'll try my best here. Looks like that. And this function is smooth. It is smooth everywhere. So here's what I'm actually going to say about smoothness. Smoothness is a necessary but not sufficient condition for being differentiable. So a function needs to be smooth to be differentiable, but that might not be enough. In this case, it's not. Because well, in fact, let's take a look. Our derivative here, if our function is x to the 1/3, our derivative is 1/3 x to the negative 2/3. And if we rewrite that as 1/3 x to the 2/3, if you try plugging in 0, we're again dividing by 0. So here, f prime of 0 is undefined. So this function, f of x equal to the cube root of x, is not differentiable at 0, or worded another way, is differentiable everywhere but 0. I will point out, this function does have a tangent line at the origin, has a vertical tangent line. So the issue here versus the previous one is, right, you typically talk about the derivative of a function being the slope of the tangent line. Well, here the tangent line is vertical and the slope of a vertical line is undefined. So definitely f of x equal to the cube root of x has a vertical tangent line at the origin. Sorry, something else I was about to say and I've completely forgotten it. Vertical tangent line at the origin. Oh, and the slope of a vertical line is undefined. Yeah.
Wouldn't this be true for any odd root?
Yeah, it would.
All odd roots are continuous, but not infinite.
If it's just the if it's just the odd root of x and nothing else has changed. Yeah, 5th root of x, 7th root of x, 9th root of x, all those would have the same sort of continuity, but not differentiability at the origin. Yeah. Okay. Sure. One more. So let's say we had piecewise functions. Do you want it to be differentiable? Do you want it not to be differentiable? Sure. So let's look at the following. Do this. So let's say we have the function that is equal to e to the x when x is less than 0. It's not to be very exciting, but fine. Equal to, make it a little more interesting. Let me think for a second. Sorry, x squared. Brain work. Sorry, it's hard to just make these up sometimes. Well, let's see. X squared plus x when x is greater than or equal to 0 and less than or equal to 2, and 3x minus 5 when x is bigger than 2. So first question, is this continuous at x equal to 0? So technically, if you're showing continuity, you should show all three things. You should be precise. You shouldn't just be like, I plug in 0 to one thing, I get e to the 0, which is 1. Oh, it's not. I messed up. I need to so I wanted to be continuous, but it's not. I need to add a +1 there. Sorry. Okay. So if I plug in 0 to the first thing, e to the 0, which is 1. Plugging 0 to the middle thing, it's 0 plus 0 plus 1, which is 1. But really, you should be like, f of 0 is 0 plus 0 plus 1. The limit as x approaches 0 from the left. We're going to use e to the x. You get e to the 0, which is 1. The limit as x approaches 0 from the right of x squared plus x plus 1 is 0 plus 0 plus 1. So then it all checks out. The limit exists, the function exists, and they're equal to each other. So yes. How about an x equal to 2? So again, same idea. F of 2 would be 2 plus 2 plus 1. Sorry, 4 plus 2 plus 1, which is 7. And the limit as x approaches 2 from the left, you'd use the same piece of the function. You plug in 2, 2, 2, you get 7. The limit as x approaches 2 from the right, doesn't look like it's going to work out. You're going to get 6 minus 5, which is 1. So, is this function continuous at 2? No, definitely not. Is this function differentiable at 2? Absolutely not. Because to be differentiable, you had to have already been continuous. Continuity is a necessary condition for differentiability. So if it's not continuous at 2, it's automatically not differentiable. I want to actually stress this because it's important. If someone ever says a function is differentiable everywhere, then you get to automatically make the assumption that the function is continuous everywhere. And sometimes people definitely like later on, maybe not later, maybe soon, when you talk about like the mean value theorem, there's an assumption that the function is differentiable everywhere, and then we use the fact that it's also continuous to grab some more stuff. So definitely be aware, people are going to say something's differentiable everywhere, and then use the condition that it has to also be continuous. So differentiability implies continuity, not the other way around. Continuity does not imply differentiability necessarily. Right? The function's continuous. We just saw 3 examples of functions being continuous and not differentiable everywhere. Yes.
It is unnecessary for continuity, right?
No, it does not, as we've seen. It's differentiability is a sufficient right. If it it's a sufficient condition for it. But it's not. So actually let's change the second piece so it is continuous. So let's, instead of saying it's 3x minus 5, let's say that it is 3x plus 1. So we're going to cross this out. We're going to make it 3x plus 1, and then it is going to be continuous at 2, because if we take the limit from the right hand side now, limit of 3x plus 1 is going to be 6 plus 1, which is 7. So then the limit will exist, function will exist, and they'll be equal to each other. So this new function, I know it's not. So now, yes, we have continuous at x equals 2. So now, even though it's continuous all the way through at 0 and at 2, it's still not necessarily going to be differentiable. So how do we show the function is differentiable at 0? Because it is differentiable at 0. Well, we're going to take the derivative from each side. So, excuse me. So our derivative is going to be e to the x when x is less than 0, and it's going to be 2x plus 1 when x is greater than 0. I don't want to say greater than or equal to 0 because at 0 things are a little bit dicey. So to see if the derivative actually exists at 0, to find f prime at 0, what I'm going to do is I'm going to just make sure that the limit from either side exists. So to find f prime of 0, the limit as x approaches 0 from the left of f prime of x is the limit as x approaches 0 from the left of, well, the derivative on the left of 0, which is e to the x. Plug in 0, you get e to the 0, which is 1. The limit as x approaches 0 from the right of the derivative is the limit as x approaches 0 from the right of 2x plus 1, which is 0 plus 1. So basically, the way you show that a piecewise function is differentiable is you just take the derivative from either side and make sure that their limits are both approaching the same value. On the other hand, this function is not going, at least unless I really ended up doing it. No, it's going to be good. This function is not going to be differentiable at 2. So if you take the derivative, f prime of x is equal to 2x plus 1 when x is bigger than, when x is less than 2. Oh, sorry, thank you. So the derivative of this part when x is less than 2 is just approaching 2 from the left. I'm really kind of thinking about that. And the derivative is equal to 3 when x is bigger than 2. So now if I approach 2 from the left, limit as x approaches 2 from the left of the derivative is the limit as x approaches 2 from the left of 2x plus 1, which is 5. Whereas on the other side, limit as x approaches 2 from the right of f prime of x is the limit as x approaches 2 from the right of 3. And the limit of 3 is just 3, and those aren't the same. So the limit from the right and limit from the left aren't the same. The limit overall doesn't exist, which means the derivative of this between the limit of the derivative. So this function is not differentiable at x equals 2. So that's how you show a piecewise function either is or isn't differentiable at a particular point, by just taking the particular pieces and taking their derivatives and then seeing, do their derivatives approach the same value or do they not? Essentially what you're kind of asking is, when you graph this thing, do you have a pointy point or not? So, right, if you actually graph this, well, let's instead of trying to make James graph it and doing a semi-okay job, we can just throw it up on Desmond's here. Just so you all can see. Maybe if I can go the right way. Yeah, cool. So if we actually graph this thing, okay, I can show you guys some neat tricks too. So let's say I want e to the x. I think I've shown you this before, but maybe not. But I don't want all of it. I just want when x is less than 0. So I'm going to do 0. Cool. And then I want x squared plus x plus 1. And I want that when x is between 0 and 2. So I want 0 less than or equal to x less than or equal to 2. Cool. And look at that. The slope of those things look like they're matching up, right? The slope here of the tangent line is getting closer and closer to 1, and it just smoothly goes over to the next piece. I mean, I have to pick on the other function, but you get the idea. Whereas, if we look at the next piece, which I altered to be, what was it again? It was 3x plus 1. When x is bigger than 2. Now, it's not super easy to tell, but I think we can tell if we zoom in here that that is not a smooth transition. Right? I have to actually kind of look at it from over here to see it. Yeah, you can totally tell that's a quarter, right? Not a nice sloping. So definitely not differentiable there because we have a corner. Yeah, it's kind of great.
Second derivative.
Same process. Yeah.
Just define the function in terms of the derivative and then take the
Yeah.
derivative of that and then
Yep.
take away from
Yep.
sides. Okay.
Okay. Cool. It's fun. If I can do the thing. I'm not sure. Okay. So just as a quick kind of, yeah. So I just want to point out, now someone could ask you all sorts of product and quotient rule questions that are kind of fun. Like someone could say, what's the derivative of x to the 4th power times secant of x? And we could use the product rule and get 4x cubed times secant of x plus x to the 4th times the derivative of secant of x. I do encourage you, at least the first few times you use the product rule, if you haven't been already, you want to kind of think of this as one piece, think of this as another piece, functions f and g, or u and v, or any two letters you like. And then here's your f prime times leave g alone, plus your leave f alone times g prime. It's always that kind of deal. Yeah. It's a great question. We're going to get there. We'll get there in a minute. That's what we're moving towards. So then we could also do something like take the derivative of, I don't know, something gross like tangent of x plus x to the 3rd over sine of x minus x squared. Now, what I would say is if someone gives you a question like this, you shouldn't simplify it unless you're specifically asked to, or unless it's really easy to and it makes sense because you have to type this gross thing into web work. But if you're just given a problem like this on a test, you should just write it out and not simplify it unless someone really, really asks you to. So here, I'm just going to use the quotient rule. So it's going to be the bottom thing. And since it's a subtraction, I need to put parentheses around it. Times the derivative of the top. The derivative of tangent is secant squared of x. And the derivative of x cubed is 3x squared. Subtract and then do the reverse. So I did bottom derivative of the top. Now I'm going to do the top times derivative of the bottom. So I'm going to do tangent of x plus x cubed times the derivative of the bottom, which is derivative sine of x is cosine of x, minus the derivative of x squared is 2x. All divided by the denominator, quantity squared. Not too terrible. I mean, it's a little terrible, but it's not too terrible. Oh, I should give you guys that. So what I'll say is, if you want some more practice doing terrible product quotient, and we'll soon see chain rule problems, I believe there is a derivative worksheet on Canvas for this class that has like maybe 30 or 40-ish problems and then also answers posted. It's good to do. It's definitely good practice. It is, you have to practice this to get good at it. It's not just going to come from seeing it. I do, and there's no way, like, I mean, I can let you guys work on it here, but like, I feel like you want to see more things. But you definitely need to spend the time doing problems so that you are a proficient differentiator. Because not that there aren't other things to learn in this class, but moving forward into 21B, your ability to quickly, accurately take derivatives is going to be probably the most important skill you have moving to the next class. Because you're going to have to be able to be confident to undoing that process in the future. So definitely make sure you spend some time, maybe we'll spend some time next class just doing derivatives. But definitely make sure you spend some time practicing derivatives, doing derivatives of things that are relatively complicated because you want to be good at it. You should definitely be able to, at this point, differentiate x to any power, and definitely be able to differentiate sine, cosine, tangent, secant, cosecant, cotangent. All those functions should be in your list. And then we're going to get like, there's going to be like a few more things that we're going to add to the list, but that's kind of it. And then just using these rules of product rule, quotient rule, or a combination of the two. Like, for example, the derivative of, I don't know, something gross like x to the fifth cosecant of x over x to the fourth plus 9. So now, not only do we have to use the quotient rule, we also have to use the product rule when we differentiate the top part. So using the quotient rule, it's going to be the bottom times the derivative of the top. Oh, got to use the product rule. So the derivative of the top is going to be 5x to the fourth times leave cosecant alone, plus switch it up, leave the x to the fifth alone, multiply by the derivative of cosecant of x, which is negative cosecant of x times cotangent of x. I do recommend putting parentheses around that because otherwise it's going to look like you have x to the fifth minus cosecant of x times cotangent, when it should be times negative. Really what you should do is just pull the negative out in the front, but it's already getting the plus sign, so it's kind of stuck. And then subtract and do it the other way around. We did bottom times the derivative of the top. Now we're going to do top times the derivative of the bottom. Or you could write it as the derivative of the bottom, right? I always do it as the, when I'm doing the quotient rule, for some reason, I always do it as the not derivative of the thing times the derivative of the thing. So I'm doing the bottom, derivative of the top, minus the top. I think it's just because it's easier to say. Times the derivative of the bottom. Now I don't need parentheses here because the derivative of the bottom is just a single piece. It's a 4x cubed. I don't need any parentheses really because it's just a thing times a thing times a thing. There is no addition or subtraction to kind of have to distribute across. Finally, divide all that garbage by the bottom thing squared. Gross. Okay. Well, we could do more of this. There are lots more things to get to. So, well, we are going to do more of this, but in a very specific way. So let's say we want to take the derivative of a product of three things. Sure. Let's say, so even though we haven't fully talked about e to the x, we did talk about it enough that I'm perfectly fine reminding you all that the derivative of e to the x is e to the x, which is great. It's a lovely derivative, kind of wonderful. So let's say we wanted to find the derivative of this product of three things. X to the sixth times e to the x times cosine of x. So here's the long way. Well, actually, let me just show you. So if I want to take the derivative in general of f times g times h, the way people typically do this is, I don't want to say this. The product rule is a binary operation, meaning you take two inputs, you get one output. So when you have three inputs and you're trying to use a binary operation on three inputs, you have to break it up so you have two inputs. So what we're going to do is we're going to think of this f times g as just one thing. And that's usually the plan of attack for any kind of thing where you have a thing that takes two pieces and gives you one output. I'm trying to think of another good example, and I'm not coming up with one at the moment, so I'll just live with that. Sorry. So product rule, great. I have the derivative of something times h. So I know that the product rule says, okay, do the derivative of the first piece. Great, there's the derivative of the first piece times the second piece, plus switch it up. Leave the first piece alone, and then multiply by the derivative of the second piece. Awesome. But now we see that we still have the derivative of f times g. So then we're going to use the product rule again, because we have the derivative of a product. So that's going to be, well, the usual product rule. It's going to be f prime times g plus f times g prime times h plus f times g times h prime. And distributing the h, we get f prime times g times h plus f times g prime times h plus f times g times h prime. And that is what is typically called the triple product rule. I do not think you need to memorize this, and we'll say why in just a minute. But let's actually apply it here. So when I see this sort of thing, I'm thinking, okay, essentially, I'm going to get three pieces, and in each piece, I'm going to get one derivative and the other two left alone. So I'm going to get derivative of x to the sixth times the other two pieces, plus the derivative of e to the x, which is e to the x, times the other two pieces, plus the derivative of cosine of x times the other two pieces. So x to the sixth times e to the x times negative sine of x. And that would be my answer, and I would totally leave it like that. I didn't want to do any factoring, although I totally could factor out an x to the fifth e to the x if someone wanted me to. Here's what I want you to know. This triple product rule can actually be generalized to a product of any number of things. So you've got a product of 4 things, or 5 things, or 6 things. The pattern is always the same. The pattern being, if I'm taking the derivative of 3 things, I should say, sorry, I'm taking the derivative of the product of 3 things. I'm going to get 1, 2, 3 pieces, and each piece has one derivative, and the other thing's not derivatives. And each piece gets its derivative taken one time. So we could analogously say, well, great, that means the derivative of a product of 4 things, f, g, h, and j. I don't know why I don't use I, but it's pretty common to not write I as a function for some reason, is going to be f prime times g times h times j plus f times g prime times h times j plus f times g times h prime times j plus f times g times h times j prime. Product of 4 things, 1, 2, 3, 4 pieces, and each piece has one derivative and the other 3 not derivatives, and each function gets its derivative taken once. Yeah. That's where we're going next. Yeah, that excellent question. So the reason we actually care about this product rule of 4 things or 5 things or lots of things is because it's going to lead us to the chain rule. Specifically, I should say the power rule version of the chain rule, and then we'll generalize it to the actual chain rule. But let's talk about if I want to take the derivative of specifically f of x to the nth power. Or as I'm going to write it a little bit more easily, the derivative of f times f times f times f n times. Great. We just talked about how to do this. We have n things multiplied together. So we're going to get how many pieces? N of them. And each piece is going to have one derivative and the rest not derivatives. The rest being the other n minus 1, excuse me, factors. So my first piece is going to look like f prime times f times all the way, right, all the f's. Plus the second piece is going to look like f times f prime times all the f's. Plus my third piece is going to look like f times f prime times all the f's. All the way to my last piece being, can I fit this in here? Maybe. F times all the way to the last one being f prime. Cool. And whoops, sorry. I always get off here. And just like you all told me, there's exactly n of these. N pieces added together. But here's what we really want to see. Each piece that's being added together is the same. The first piece is f prime times f to the n minus 1 power, because you have f times f times f n minus 1 times, right? There are n minus 1 f's here. And here, there are also n minus 1 f's, and so on and so on. All of them have n minus 1 f and 1 f prime. So we can actually write is we have f to the n minus 1 power times f prime plus f to the n minus 1 power times 1 f prime plus all the way to f to the n minus 1 power times 1 f prime. And we still have n of those. So then if you have the same thing added together n times, you just have n times that. Right? Just like you have the same thing added together 5 times, you have 5 times that. So this is really equal to n times f to the n minus 1 times f prime. Or written in the more functional notation, the derivative of f of x to the nth power is n times f of x to the n minus 1 power, power rule, times the derivative of the inside stuff. And that is the power rule version of the chain. The chain rule version of the power rule. I don't remember what they say. There's both things together at once. We'll talk about the more general version in a bit here. So we can now use this to take derivatives of things raised to really, really high powers. For example, well, actually not for example. What I would say first is, in the past, if someone had asked you to maybe say, find the derivative of 6x cubed plus 1 to the second, you can just multiply that out, right? Totally not terrible to multiply out. You have the derivative of, let's see, 6x cubed times 6x cubed is 36x to the 6th. And then 6x cubed plus 6x cubed is 12x cubed. And then 1 times 1 is 1. And then the derivative of that's going to be 36 times 6. Okay, fine. 216x to the 5th plus 36x squared. Great. But we don't have to do that anymore. We can just say, well, look. And now here's where I'm going to introduce some language that I use all the time that I want you to use too, because I think it's good. I have the derivative of some stuff squared. I use the word stuff all the time. Stuff is like the best word in math. I have the derivative of stuff squared. I know the derivative of x squared is 2x. So I know the derivative of some stuff squared is 2 times my stuff to the first power, if you want to really think about the power rule there. But then we have to multiply by what? The derivative of the stuff, the derivative of the inside, the derivative of 6x cubed plus 1. So I've got 2 times my stuff to the first power times the derivative of my stuff. And I really, really, really would like you to think of it that way. There's my stuff, or my inside for the word inside. There's the derivative of my stuff. And not that you should simplify this, but I will point out that if we do simplify this, it is the same as, in fact, actually, I'm going to go backwards. I'm going to simplify this. I'm going to factor out a 36 from each of these. So this is equal to 36 times 6x to the 5th plus x squared. Maybe I should pull out an x squared as well. That's equal to 36x squared times x cubed plus 1. Sorry, 6x cubed plus 1. And then I could rewrite this if I really wanted to as 2 times 6x cubed plus 1 times 18x squared. They're the same for real every time, which is great. Because then you can do some crazy stuff like, instead of taking the derivative of 6x cubed plus 1 squared, you can say, what's the derivative of 6x cubed plus 1 to the 1000th power? Which we definitely don't have the time to multiply out. Right? That's a lot of terms. 1001 terms. You should never multiply that out. That would be insane. Instead, we'd be like, oh, I've got some stuff to the 1000th power. The derivative is 1000 times my stuff to the 999th power times the derivative of my stuff. And my stuff is the same. It's 6x cubed plus 1, and its derivative is still 18x squared. And I really wouldn't suggest simplifying this in any way, shape, or form. Maybe if you really wanted to, you can rewrite it as 18,000x squared times your stuff to the 999th power. But I don't think you should really, unless you're being asked to, because writing it this way specifically indicates that you understand that you are using the chain rule. That you are at the end multiplying by the derivative of the inside stuff. And I think it's important to demonstrate that you are aware of what you're doing there. So I would like you all to find the following derivative. Find the derivative of, sure, sine of x plus 9x squared to the 21st power. Don't worry, I didn't forget about the e to the x and the natural log of x. We're rolling back around to there, as well as the inverse trig functions, which, yeah, we'll see about it. They're coming back around. So there's a few things you still have to build up before we get there. Let's see. One of these, yeah. I should look for something here real quick. Yeah. So here, again, same sort of deal. You've got some stuff to the 21st power, the derivative of x to the 21st is 21x to the 20th. I'm just using the same idea. The derivative of stuff to the 21st is 21 times my stuff to the 20th power, and then we multiply by the derivative of the stuff. Do make sure that the inside stuff doesn't get changed, right? The inside stuff just stays the same. And then on the outside, after you have done the derivative of the outer part, multiply by the derivative of the inside part, which is cosine of x plus 18. What I'm trying to help you avoid doing, I've definitely seen people write the answer to this incorrectly as 21 times cosine of x plus 18x to the 20th power. Right? They do the derivative of the inside stuff, but they do it on the inside when you should do it on the outside. Questions? Sure, yeah. So you're thinking something like, in fact, like something like the derivative of sine of x plus sine squared of x. Is that kind of what you're thinking? Oh, I'm sorry. Is that kind of what you mean? Yeah. So specifically, when I have a trig function to a power like this, it's not so bad here, but I do kind of recommend, I usually like to rewrite this as the derivative of sine of x plus sine of x quantity squared. So that I know that, oh, I've got something squared. So if I want to take the derivative of this, the derivative of sine of x is going to be cosine of x. And the derivative of sine x squared is going to be, well, some stuff squared. The derivative is 2 times my stuff times the derivative of my stuff is also cosine of x. I will point out, because it comes up often, you might see people simplify this as sine of 2x. Because that's a trig identity. Sine of 2x is equal to 2 sine x cosine. In fact, we'll come back to that. That's a good example for something else we're about to see in a minute here. Yeah, all right. What I want to say about this is they do get more complicated. Like someone might ask you to find if your function is, I don't know, let's say it's tangent to the 5th power of x cubed plus sine. Oh, I'm getting ahead of myself here. I am getting ahead of myself, yeah. Yeah, sorry, I gotta take another trip first here. One moment, please. So before we can really do more, we need the general version of the chain rule. Right? We just have the power rule version. So the general version, let me show you an example. So let's find the derivative of sine of not x, but sine of 2x. And instead of doing it the way we might already know how to do it, I'm going to show it to you graphically. So here's the graph of sine of 2x. Sine of 2x looks a lot like sine of x because its period has been cut in half. Sine of x is a period from 0 to 2 pi. Sine of 2x is a period from 0 to pi. So here's my usual sine function. Boom, 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 boom. And here's my sine of 2x function. Oh, sorry, there's sine of x. Sine of 2x has a period of pi, so it's going to have half the period, but the same behavior. So it's going to do this. It's going to start here and then go up to 1 after a quarter of a period, and then back to the middle, and then down to -1, and then back to the middle. So here's my sine of 2x function. And it continues on. Okay, so now I'm going to do the same sort of thing I did to find the derivative of sine before, which is just draw the derivative using the slopes of the tangent lines. So check this out. We know that for sine of x, the slopes of the tangent lines give you a nice cosine deal. So, right, the slope here is 1, and then 0, and then -1, and then 0, and then 1. So there is my derivative of sine, which we already knew. So there's your y prime equal to cosine. But now check this out. Here's where I think things are kind of neat. If you look at the slope of the tangent line of this red function here, it's definitely got a steeper slope than the cosine function. Or sorry, than the blue function. Apologies. It's way steeper. Now, I'll point out, still here at the top there, the slope of the tangent line is 0. So we're definitely going to, if we break this up into 1, 2, 3, 4 quarters of the period, we're definitely going to get a 0 there and a 0 there. But at this spot here and this spot here and this spot here, the tangent lines have a very positive slope, a very negative slope, and a very positive slope. And more positive than 1 and more negative than -1. In fact, the slopes are 2 and -2. Sorry, -2. And so it looks like this. So here's what this looks like. This looks like a cosine function, right? Because cosine starts at the top and then goes down and then back to the top. But it's a cosine function with a shorter period. So it's still a cosine of 2x. But it's stretched out vertically. It's had its amplitude multiplied by a factor of 2. So here our derivative is not just cosine of 2x, it's 2 times cosine of 2x. Or as the quotient rule might, sorry, not quotient, as the chain rule might suggest, the derivative here is cosine of your stuff times the derivative of your inside. It is, yeah, I wrote the wrong thing. Thank you. It's sine of 2x. Apologies. Good call. Thanks. So the idea here is that the chain rule doesn't just work for some function raised to the nth power. It really works for any function of a function. And so when I think about the chain rule, what I really think about doing is taking the derivative of the outer function, leaving the inside alone, and then multiplying at the end on the outside by the derivative of the inside. No, okay, so yes, then I know what you're supposed to do. So that's where you're going to go back to this. So another way you could show the derivative of sine 2x is what it is by writing sine 2x as a product. So the derivative of sine 2x is equal, and this is actually another good way of seeing that we said is true. The derivative of sine 2x is the derivative of 2 times sine x times cosine x. And now the 2 is just a constant, it's going to hang out. And then we use the product rule. So the derivative of sine is cosine, times leave the other thing alone, which is cosine. And then plus sine times the derivative of the other thing, which is negative sine. Now I know this might not look like what it is, but it is. The sentence made more sense in my head. No. Wait. So you mean right here?
Yeah.
So no, all I'm doing is I'm using a fact. I'm using a trig identity. So there's a trig identity that says sine of 2x, the double angle identity, is equal to 2 times sine of x times cosine of x. There's also another double angle identity, which I'm going to show you because we're going to need a second here, which is cosine of 2x. Cosine of 2x is cosine squared of x minus sine squared of x. And hey, look what we've got down here. We have 2 times cosine squared of x plus sine times negative sine is minus sine squared of x, which is exactly 2 cosine of 2x. So what I want to point out is 2 things. One, you can totally use these trig identities to show that the chain rule also works here. The derivative of sine of 2x is indeed cosine of 2x times the derivative of 2. Thing 2, if you had to do this derivative without using the chain rule, the way you would do it is use the trig identity and say, oh, that's 2 sine x cosine x, and then you would use the product rule. Now, I think if you were asked to do this on test without the chain rule, you wouldn't have to do this last step of rewriting it like this. You would just be expected, I think anyway, to leave it like this.
Yeah, but it changes twice the same function.
Definitely, if necessary.
But many times it's-
Right. So basically, here's what I always say to myself when I'm taking a derivative. If I'm taking the derivative of a function, whether it's the outside piece, the inside piece, whatever, if the piece I'm taking the derivative of has an inner piece that is still more complicated than just x, I probably need to keep doing the chain, which is why I really like the word stuff. Let me show you an example. Cool. Okay. So let's say we wanted to find now the derivative of something like tangent to the 5th of x cubed plus sine of 6x. And again, whenever I have a trig function to a power, I really do recommend rewriting it as the derivative of, tangent of x cubed plus sine of 6x, all raised to the 5th power. To me, that makes it easier to see what my outermost function is. Because when you're using the chain rule, you're essentially working from the outside in. You're taking the derivative of the outermost function, leaving the inside alone, and then multiplying by the derivative of the inside. So let me kind of show you all the steps you could take to do a derivative of a function like this. So first step, all right, I've got some stuff to the 5th power. My derivative of some stuff to the 5th power is 5 times my stuff to the 4th power. Times the derivative of the stuff. Now, some people like to actually, but I don't like writing all these steps, but I'm going to just to kind of show you. So then we're going to multiply by the derivative of tangent of x cubed plus sine of 6x. The derivative of that. Okay, so now we have to do the derivative of that. So we're going to get, we still have 5 times tangent of x cubed plus sine of 6x. The 4th. Okay, so now looking at this new piece I'm differentiating, I have tangent of some new stuff. And the derivative tangent of some new stuff is going to be secant squared of that new stuff times the derivative of that new stuff. So I'm going to get secant squared of my new stuff times the derivative of my new stuff. That's going to be secant squared of x cubed plus sine of 6x times the derivative of x cubed plus sine of 6x. And then we keep going. So then I've got, you might at this point choose to rewrite this in the abbreviated notation, 5 times tangent to the 4th of x cubed plus sine of 6x. That's totally fine. Times secant squared of x cubed plus sine of 6x. And then the derivative of x cubed plus sine of 6x is going to be, well, derivative of x cubed is 3x squared. And the derivative of sine of some stuff is cosine of the stuff times the derivative of that stuff, which is just, I don't think we need to write a whole other line for that. No, exactly. Yeah, good question. So the thing is, the 6 only gets multiplied by the thing that it is the derivative of the inside of. Yeah. Because I had to use the chain rule again. So here's the so if I would let me show you how I would do this if I was actually kind of doing it in one shot. So what I would really do is I would say, okay, if I'm taking the derivative of tangent of x cubed plus sine of 6x to the 5th power, that's going to be 5 times my stuff to the 4th times the derivative of the inside stuff. But the derivative of the inside is a whole new complicated function, right? I have to take the derivative of tangent of x cubed plus sine of 6x, which requires the chain rule again, because it's still a composition of functions or a function of a function. So I know that the derivative tangent of something else is going to be secant squared of the something else times the derivative of the something else. And the derivative of something else is 3x squared plus cosine of 6x times 6. So basically, when you're multiplying by the derivative of the inside stuff, if that inside stuff is complicated and is still a function of a function again, you have to use the chain rule again on the new of the inside of the inside. So basically, the x cubed plus sine of 6x here is the inside of the inside. So just to write these rules out, because we actually haven't written them, just so you can see them all in their glory. The way people typically write the chain rule is to say, if you're trying to find the derivative of a composition of functions, f of g of x, it's going to equal f prime of leave the insides alone times the derivative of the insides. Or as I would really, really encourage you to think of it, the derivative of a function of some stuff is f prime of the stuff, wait, differentiate the outside, leave the insides alone, multiply by the inside, the derivative of the inside. And yes, there are more complicated versions of this. You can write a chain rule for a composition of as many functions as you want. So people often do write down a derivative of like a double chain rule problem, or they write the derivative of f of g of h of x. So when I look at this, here's what I want you all to see. I'm just going to use the usual kind of thing I've been saying every time. I've got f of some stuff. So the derivative of f of some stuff is f prime of the stuff times the derivative of the inside stuff. Now check this out. I'm just going to write the derivative of g of h of x. But now you might recognize that g of h of x is itself a composition of functions, and for its derivative requires the chain rule. So then that's going to equal still the same first part that we had, f prime of g of x h of x. And then the derivative of g of some stuff is g prime of the stuff times the derivative of the stuff. So basically, you're always just, I know it looks terrible, it looks like, but the point is, every time you're differentiating a chain rule kind of thing, you differentiate the outside, leave the whole entire inside alone. Then look at the inside as this new piece and be like, okay, for that new inside, differentiate the outside, leave the inside alone, multiply, right? Keep doing it until you can't anymore. So what I'll also point out is, I don't want to say this that way. You try not to like basically, yeah. So if you find yourself saying the derivative of the inside stuff and then just being able to say what it is without having some new stuff, that's typically your stopping place. Right. So for example, if we're going to take the derivative of something like, sure, x to the 10th plus e to the 3x, yeah, sure, why not, to the 8th power. The derivative of some stuff to the 8th is 8 times my stuff to the 7th times the derivative of the stuff. Okay, the derivative of x to the 10th, you know how to do. X to the 9th. There isn't anything more complicated about that. The derivative of e to the 3x, though, it's an e to the stuff. The derivative of e to the x is what? Right, I already said it's e to the x. So the derivative of e to the stuff should be, right, I'm just taking the x and replacing it with the word stuff. Honestly, that's how I would encourage you to approach all these derivatives. Think about the derivative with an x, like the derivative sine of x is cosine x, and replace the x with the word stuff. Derivative sine of stuff is cosine of stuff. But then I said the word stuff, and so that magically makes me have to do what? Multiply by. Or do we always multiply by if I said the word stuff? Thank you. Yes, always, 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 always. So whenever you, that's why if you're saying the word stuff, you're like, oh, derivative of e to the stuff is e to the stuff. But then I have to multiply by the derivative of stuff. I said stuff. So the derivative of e to the 3x is e to the 3x times the derivative of 3x, which is 3. Oh, yeah, thank you. Yeah, sorry. I know it's always a challenge. I need like, I don't know. I need some sort of like box to keep this paper in, but it's never, I would never do it even if I had it. So. Okay, cool. So now, yeah. Yeah.
Let's do a derivative for not this.
Okay.
In general, if you don't want to go over it now, it's fine, but what if you have just like something complicated, it's all square rooted, like not too complicated, but here's an example, like x plus 1 squared plus something, all of that squared.
Sure. Yeah. That's exactly the situation. So for example, if I was trying to take the derivative of the square root of, I don't know, 2x plus 1 to the third plus tangent of 3x, I would highly encourage you to rewrite this. And this is true whenever you have a root. I would write this as all of that stuff to the 1/2 power. So now I have some stuff to the 1/2, and I can apply the power rule. I know the derivative of x to the 1/2 is 1/2 times x to the negative 1/2. So I know the derivative of some stuff to the 1/2 is 1/2 times my stuff to the negative 1/2. And then what do we have to multiply by, everybody? Right, the derivative of the stuff, the derivative of the inside. So you can either do this in one way or another. Sometimes people just like to write down the same exact copy of the stuff and like put a prime on it, because they just want to not have to think about actually doing the derivative of the next step. I don't particularly like to do that because I try not to kill all the trees in the world, but I'll do it here. So I know I have to take the derivative, and then I'm just going to do it. So then I would have really just jump down to this step and said, okay, it's 1/2 times my stuff to the negative 1/2 times the derivative of this stuff. So the derivative of 2x plus 1 to the third is 3 times my stuff to the second times the derivative of the inside stuff, which is 2. Plus the derivative tangent of some stuff is secant squared of that stuff times the derivative of that stuff. Yeah.
Some expression, then we're doing chain rule, we keep the input the same, but we change the operation. So when we have f of g of x, and we're getting the derivative of that, we are changing the operation that is operated on g of x. So meaning f turns into f prime, and then we times it by the.
Sure. Yeah, you are no longer evaluating f at the input of g of x. You are evaluating f prime at the input of g of x. Yes. Cool. So functions of functions of functions of functions. You differentiate the outside part first, you leave the inside parts alone, and then you multiply by the derivative of the inside part. The derivative of the inside part is more complicated. You just keep doing that same process until you've exhausted it. And again, I highly recommend that you practice this as much as you can, because it is one of those things you're going to use over and over and over again. Almost everything we learn is the derivative, how to take the derivative. We really want to think of the chain rule version of it. So now, when we learn any new, so there's not a lot of functions left to differentiate. We've covered most of them. X to a power, trig functions, e to the x, all of them have their chain rule version. The derivative of sine of x is cosine of x, the sine of stuff is cosine of stuff. Derivative of e to the x is e to the x, derivative of e to the stuff is e to the stuff times the derivative of stuff. Works for everything, and it works for anything new that we encounter, not that there's a lot of new stuff left. So, okay. So what about the derivative of the natural log of x? So let me ask, how did your teacher talk about it in class? Or did they? Not yet? Did yours? I think, did you, you're the one who asked about natural log of x, right? No, but who asked about natural log of x? Oh, okay. Have you talked about natural log in class? Okay, all right. That's what I was hoping she didn't do, but it's fine. So you can totally do this using the limit definition. It's nobody's favorite. So it's the limit, h goes to 0, of the natural log of x plus h minus the natural log of x all over h. I feel like this limit definition, much like the e to the x one, is a little handy, but you're kind of stuck with it. So we use our logarithm rules. Say, oh, natural log of x plus h minus natural log of x is the natural log of x plus h divided by x. And then we rewrite that as the limit as h goes to 0 of the natural log of 1 plus h over x all over h. And then I have to remember what we do next. What do we do next? Oh, we do some crazy stuff, I think. Let me think for a second here. Oh, I know what it is. I think. Sorry, it's been this one's always one where you have to like. So this is kind of like one of those examples where, like with the product rule or the quotient rule, where you kind of have to know what the answer is to be able to do this. Because unless you've seen it before, it's kind of just like, well, someone's going to pull something out of thin air and make this happen. And I'm trying to remember. I know what I want to happen. So here's what I know I want. So let's actually just work backwards from a place. I know I want E to show up, and I know that E is the limit as n goes to infinity of 1 plus 1 over n to the n. Or if you prefer, and we do prefer, the limit as h goes to 0 of 1 plus h to the 1 over h. And I kind of have something that maybe looks a little bit like that. Kind of. I have 1 plus h over x. And what I should really say about this E definition is it doesn't actually have to be h here and 1 over h here. It can actually be anything that's going to 0 and it's reciprocal. So it'd be perfectly fine to have this, but it would also be perfectly fine to have the limit as h goes to 0 of 1 plus h over x to the x over h. All these limits are in fact the number E. Fun fact. Kind of cool. So I want that there, but I'm missing the power of x over h. So I'm just going to write it in there. Kind of weird, right? So like I want an x over h up there, which means it could come down in front. So let's put it down in front first. So here's what I'm going to do, even though this feels kind of wrong. I'm going to say, well, I want an x over h times my natural log of 1 plus h over x. Now, is this the same as that? No, definitely not. What do I have extra in this next piece that I didn't have before? I would agree with that statement. Right, because I already had the h in the denominator, but I multiplied this whole thing by x. So to compensate for what I've done, I need a 1 over x to balance that out. And now I think we can all agree that this is the same as that. Yeah, it is. Okay, so now check this out. I'm going to pull this x over h up into the exponent of the logarithm I'm taking. This is the limit as h goes to 0 of 1 over x times the natural log of 1 plus h over x to the x over h. And now we're going to use one of those limit rules that says the limit of a thing, of a function of a thing, you can put the limit through the function and say it goes inside. So this is really equal to 1 over x times the natural log of the limit as h goes to 0 of 1 plus h over x to the x over h. We just said that was e. This is 1 over x times the natural log of e, which is 1 over x times 1. There's your derivative of the natural log of x, 1 over x. And now, automatically, we know that if the derivative of the natural log of x is 1 over x, the derivative of the natural log of some stuff is 1 over the stuff times. You should all say it. Everybody say it. Thank you. Times the derivative of the stuff every time. So just for a quick example here, if you were going to take the derivative of the natural log of x squared plus 1, it would be 1 over your stuff times the derivative of your stuff. And people would usually probably write that as just 2x over x squared plus 1. Yeah.
So, what is the little confusion to lay out with the sum of I equals 0?
Yeah, sure. Yeah.
Factorial of.
Yeah, yeah.
Something in factorials. I can't remember. I think.
Right.
I factorial.
Yeah, yeah, you can define E, although I wouldn't in this class as the sum from k equals 0 to infinity of, I guess you don't want to start at 0 really. Maybe you do, but fine. Of oh my gosh, sorry. Oh my gosh, sorry. Apologies. I'm just, so e to the x is the sum from k equals 0 to infinity of x to the n over n factorial. So I want e to the 1, I just want the sum of 1 over n factorial. Which is not the best way to define it in this class. I will point out, so it is true that e is equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, so on and so on and so on. Is that how your professor defined it?
How is the first one defined? Because if k is 0, how is the first one defined?
Because 0 factorial is defined to be equal to 1, not 0. For the same reason, or the same sort of reason, that 5 to the 0th power is equal to 1, because the additive law of exponents says it has to be for the rules to work the way they need to work, right? We need 5 to the 0 equal to 1 because we know that 5 to the 0 times 5 squared, you have to be able to add those exponents together and get 5 to the 0 plus 2. So 5 squared times something equals 5 squared. That something had better be 1. You have no other choice. For the same sort of reason that this has to be 1, 0 factorial is also defined to be 1. Because otherwise all these other things that depend on it don't work the way they need to work. It really, in my opinion, the best way to understand why this is when you take a stats class and learn about probability and talk about the choose function, of the number of ways you can choose so many things out of so many things. So I'll just point out very, very briefly that if you want to know the way of taking, like, let's say you had 4 different people and you wanted to pick 2 of them to be in a group. How many ways can you pick 2 people? 6. So let's say it's the 4 of us. It could be me and her, me and you, or you and you, or you and you, or you and you. 6 ways. And the way you can calculate that really easily is by what's called the choose function for choose 2, which is written in this way. Don't worry about this. You don't need to write this up, but I just want you all to understand what's going on here. This is 4 factorial over 2 factorial times the difference between them. It's 4 minus 2 factorial. By the way, factorial, just number times all the lower numbers down to 1. So 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 2 factorial is 2 times 1. And you get 24 divided by 2 times 2, which is 6. Okay, so it works. And here's what I want to ask you. Same 4 people. How many ways out of us 4 people can you choose all 4 of us? 1 way. I pick 1, 2, 3, all 4 of us. So here's what I want to point out. 4 choose 4, which if you calculate the same way, it's the top thing factorial over the bottom thing factorial and the difference between them factorial. That better work out to be 1. Well, that's 24. That's 24. This 0 factorial here had better be 1. So that's the reason I always use to justify why 0 factorial has to actually be 1. Because otherwise this whole thing that works and is true wouldn't work. It's kind of weird, but yeah, 0 factorial is 1. Okay, so natural log of x, derivative is 1 over x. Definitely want to memorize that for sure. And in a similar way, the derivative of the natural log of some stuff is equal to 1 over the stuff times the derivative of the stuff. Okay. Logs of their bases, there's a couple of different ways to get there. The easiest way for a log with a different base is to use the change of base formula. So it is true that log base, I don't know, 2 of x, or whatever base you like, you could totally rewrite this using any base you want. Excuse me. I'm going to use everyone's favorite base, the natural base, base e. I'm going to write this as the natural log of x over the natural log of 2. What else is the change of base formula good for? Well, if someone ever asked you to find, say, like, I don't know, log base 4 of 8, which says 4 to what power equals 8, we can recognize that 4 and 8 are both powers of what common base? 2. So you could totally, instead of doing some other stuff, like you could do it this way. You could say log base 4 of 8 equals x, 4 to the x equals 8, 2 to the 2 to the x equals 2 to the third, 2 to the 2x equals 2 to the third, 2x equals 3, x equals 3 halves. That's one way of getting there. But the other way of getting there is using the change of base formula and say, oh, well, I'm just going to use base 2. And it's going to be log base 2 of 8 over log base 2 of 4. Log base 2 of 8 is 3. Log base 2 of 4 is 2. 4. The reason I'm mentioning this is not because I really care about this, but just because I want you to see the change of base formula works. And it's always pick whatever base you want, log of with that base of the top thing, or the thing that looks like it's higher up, over log of your new base of the previous base. So when I think about the change of base formula, I think about the fact that this 2 looks like it's lower, so it ends up in the denominator. And this x looks like it's higher, so it ends up in the numerator. But look what we really have. What we really have here is a constant, 1 over natural log of 2, times a function, natural log of x. And whenever you take the derivative of a constant times a function, the constant just hangs out. So if I'm trying to find the derivative of log base 2 of x, it's really going to be the derivative of this constant times the natural log of x. And that constant hangs out, you get 1 over natural log of 2, and then the derivative of the natural log of x is 1. So generally, if you have a base other than e, the derivative of log base a of x is 1 over x times the natural log of that base. That's the general formula for log derivatives of logarithms of other bases. So this is not, there's another way to see this we'll talk about, but there's another thing we have to talk about first before we can get there. What I'll say about this is if you want to take, say, for example, the derivative of the natural log of x to the 4th plus sine of x, it's going to be 1 over your stuff times the derivative of your stuff, which you could, and probably most people do like to write as 4x cubed plus cosine x over x to the 4th plus sine of x. Either way, it doesn't really matter. I mean, it matters as far as how much space you're taking up. Whereas if you're trying to take the derivative of, say, log base 6 of x to the 4th plus sine of x, then you would get the same sort of thing, 1 over your stuff times the derivative of your stuff, but then you would also, in the denominator, need a factor of natural log of 6. I usually write it at the end as this. Now, most people will probably put this all together and write it as 4x cubed plus cosine of x over x to the 4th plus sine of x times natural log of 6. So the general rule of thumb is whenever you're taking the derivative of a logarithm with a base other than the natural base, you always end up dividing by the natural log of that base. In fact, I guess you could say that rule is always true, because if your base was e and you divide it by the natural log of e, you'd just be dividing by 1. You can change anything. Question.
So can the base ever be a variable itself?
I don't think that's a function we typically think about. Yeah, that would be strange. If the base, well, it depends on what I guess it depends on what you're writing. Like, so if you said your function was log base x of what? Yeah, I don't know if we have a way of really. I think I don't know. I've never thought about that question. I've never seen anyone ask that question. So I don't have a good idea about that. I'll ask my friends, see if we have any thoughts. But at this point, I would say you definitely don't need to worry about it because no one's ever going to ask you about this. But interesting question. So, okay, here's where we're going next. So really the way most people talk about the derivative of either the log of x or the of x is through what's called implicit differentiation. So the idea here, and we got 10 minutes, we can talk a little bit about this. So the idea is sometimes there are functions, well, there are things that are not functions. Let's go with this example first. So let's say here's something that is not exactly a function. X squared plus y squared equals 20. Definitely not a function. It's a circle. I mean, it's grounded in a circle, which certainly violates the vertical line. But that doesn't mean that we couldn't find slopes of tangent lines anyway, right? That circle, except for at a couple points, definitely has a tangent lines where the slope is defined almost always, except for like right there and right there, we'd have vertical tangent. So specifically, if I'm going to look to the point, I don't know, 4, -3, which is definitely a point on this circle, I would love to know what the slope of the tangent line is there. Now, sometimes you have the ability to actually solve for y as a function of x and then figure out what the derivative is. And that would totally work here. So I could, in one way, which is not always an option, but in this case certainly is, we could say, oh, I'm going to solve for y squared equals 25 minus x squared. And then taking the square root of both sides, y is plus or minus the square root of 25 minus x squared. And in this particular point, I'm using the bottom half of the circle. So specifically, I'm using y equal to the negative square root of 25 minus x squared for the bottom half of the circle. So if I want to find the slope of the tangent line there, I'm going to take the derivative. So I'm going to find dy dx. Oh, I should really write this before I write dy dx. I should say I'm going to write this as negative 25 minus x squared to the 1/2 power. So it's easy to differentiate. So my derivative here is going to be negative 1/2 times my stuff, right? Using the chain rule to the negative 1/2 power times the derivative of the inside, which is negative 2x. And I'm going to simplify this. The negative 2's cancel, and I just end up getting x times 25 minus x squared to the negative 1/2. Whereas I'm going to write x over the square root of 25 minus x squared. And now let's plug in the point. So if I plug in the point 4, -3, I'm going to get 4. Well, I don't have to plug in the -3. I'm just plugging in the 4. I get 4 over the square root of 25 minus 4 squared, which is 4 over square root of 9, which is 4 over 3. Which certainly looks like a plausible answer for the slope of this tangent, right? It's definitely positive, looks okay. That's a lot of work. And it's more work than we actually need to do. So here is the alternative. We're going to assume, although it's not entirely true, but we're going to do it anyway. We're going to assume that y, people often say assume y is a function of x. We can be more general, say assume y depends on x. But really, we're assuming it's a function of x, even though it's not. So y is kind of like f of x. In fact, I might write that down. So now I'm going to rewrite this equation, which you can't see anymore because I've done this, as just to be super extra explicit about it, x squared plus f of x squared equal to 25. And instead of solving for f of x or for y, I'm not. I'm just going to take the derivative of both sides right now. What's the derivative of x squared? Okay. This is why we talked about the chain rule. What's the derivative of some stuff squared? Right. And actually, I want to be super clear. 2 times my stuff to the first, because I want you to make sure that if your power is higher, you recognize the new power should be 1 less. So 2 times my stuff to the first, and then yes, times the derivative of my stuff equal to 0, the derivative of the other side. But now I'm going to write it the way people actually write it, which is what I really have is x squared plus y squared equal to 25. And when I take the derivative of both sides, I get 2x. The derivative of some stuff squared is 2 times my stuff times the derivative of my stuff equal to 0. Same thing, I'm just using y and y prime instead of f of x and f prime of x. Literally the same thing. I'm just using a different letter for my function. But now if we solve for y prime, check it out. 2y times y prime equals negative 2x, and y prime is going to equal negative 2x divided by 2y, which is negative x divided by y. And then if you plug in your point, 4 comma negative 3, you get y prime evaluated at 4 negative 3 equal to, well, let's see, negative 4 over negative 3 is positive 4/3. Oh, it's the same. And this is considered to be an easier way of getting there. Because, well, I shouldn't say it's an easier way. Sometimes it's the only option. Let me show you what I mean. Yeah, I got time. So let's look at some other, so this is, I'm sure, an example in your book. This next one, it's a classic example of a equation that we can't solve for y for. I have to remember what it is. I do have to remember what it is. I think it's x cubed. Let me look. Pretty sure it's x cubed minus 6xy plus y cubed equals 0. Or I suppose, let me see. Yeah, that's fine. Okay, sure. That's one way of writing it. I think sometimes it's written as x cubed plus y cubed equal to 6xy. And I know 2 points on this graph. One of them is the origin. One of them is the point 3 comma 3. Plug in 3 comma 3, you get 27 plus 27 equals 6 times 3 times 3, and that definitely works out. Check. So here's what this kind of looks like. Also, I would definitely recommend graphing this on Desmos. It's super neat. It looks kind of like this. It's got some symmetry across the line y equals x, which makes sense because if you interchange x and y, it's the same equation. You got the point 0, 0 there, and you got the point 3, 3, comma there. And the idea here is that I would love to find the slope of the tangent line at 3, comma 3. And there is absolutely no way I can solve this equation for y. It's impossible. Cannot be done. So maybe not. It might not be impossible. It's too hard. We don't want to do it. We have a better way of doing it. I think it might actually be possible. Fine. I don't care. So what I'm going to do is I'm going to find y prime implicitly. I'm going to make the assumption, the implicit assumption, that's why it's called implicit differentiation. It's implied but not explicit that y is a function of x, and take the derivative of both sides. Again, thinking of y as some f of x and x is just good old x. So I should really say, when we differentiate both sides, you're differentiating with respect to the variable x. X is our independent variable. So the derivative of x cubed is just 3x squared. But y is a function of x. So the derivative of y cubed is going to be 3y squared times my derivative. So I've got the derivative of x cubed. Differentiate both sides. Derivative of x cubed is 3x squared. The derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. On the right-hand side, we're going to have to use the product rule. I have 6x, a function of x, times y, a function of x. Right? They're both functions of x. Y implicitly. So using the product rule, what's the derivative of 6x? Times, leave the other thing alone. Okay, here's the fun part. It's 11:50. You gotta go. We're almost done. 6x left alone, and now times what's the derivative of y? The derivative of y. kind of annoying, but the derivative of y is the derivative of y. Derivative of y. And then, so then if you just want to find the slope of the tangent line at 3, 3, you could plug in 3 for x and 3 for y right now and solve for y prime. But if you want to find the derivative in general, because maybe you want to find the slope of the tangent line at some other point, like 0, 0, although 0, 0 is not great, you would solve for y prime. So we're going to take this and this, put it on the same side. 3y squared y prime minus 6xy prime equal to 6y minus 3x squared. Factor out of y prime. And then divide by that. So you get y prime equal to 6y minus 3x squared over 3y squared minus 6x. Usually you don't have the option to do anything after this, but in this particular example, you can factor out a 3 from the top and the bottom and get 3 times 2y minus x squared over 3 times y squared minus 2x. So we get y prime equal to 2y minus x squared over y squared minus 2x. And the slope of the tangent line at 3, 3 is 6 minus 9 over 9 minus 6, which is -1, which looks pretty valid. Okay, next time we'll use this implicit differentiation to talk about, again, the derivative of the natural log, the derivative of e to the x, and I think we can get to the inverse tangent, the inverse trig function.